In Module 6.4, we discuss the role of bone remodeling and its importance in two of the major functions of the skeletal system, namely, its role in support and its role in storage of minerals, for example, calcium. We also briefly discuss bone repair following fractures. Let's begin now. The process of bone remodeling continuously recycles and renews the organic and mineral components of the bone matrix. Recall from Module 6.1 that the skeleton has 5 major functions, namely support, storage of minerals and lipids, blood cell production, protection, and leverage. 2 of the 5 major functions of the skeleton depend on this dynamic nature of bone, namely its role in support and its role in storage of minerals. Now, in adults, the mature bone cells called osteocytes maintain the bone matrix surrounding their individual lacunae. They continually remove and replace calcium salts from the extracellular matrix. Osteoclasts and osteoblasts are also active, even after bone growth has finished or epiphyseal closures have occurred. Normally, their activity is balanced. That is, as one osteon is formed by osteoblasts, another is destroyed by osteoclasts. And apart from conditions due to disease or the effects of aging, the activity of osteoclasts and osteoblasts typically offset each other. The ability of bone to remodel, that is, to build new osteons and to remove existing bone matrix, is quite high. We could say that the turnover rate for bone matrix is quite high. In young adults, almost 1/5 of the skeleton is recycled or replaced each year. Now, not every part of every bone is affected at the same rate. For example, the spongy bone in the head of the femur may be replaced 2 or 3 times a year, but the compact bone along the shaft remains largely untouched. First, let's talk about the role of bone remodeling in terms of the role of the skeleton in providing physical support. The ability of bone to remodel or to turn over its minerals gives bone the ability to adapt to new stresses that occur at different stages in life. For example, heavily stressed bones are thicker and stronger, whereas bones receiving lower than normal stresses are thinner and more brittle. Thus, regular exercise, including weight resistance training, can be very important to maintaining bone structure, whereas inactivity can lead to degeneration. Degenerative changes take place in the skeleton after even brief periods of inactivity. For example, inactivity due to a broken limb, being in a cast, or the removal of weight bearing, such as when using crutches, results in loss of bone mass. After even a few weeks, the unstressed leg will lose up to about 1/3 of its bone mass. However, the bone rebuilds just as quickly once they again carry their normal weight. Bone remodeling is very important for a second major function of the skeleton, namely, the skeleton serves as storage for minerals such as calcium and phosphate. Calcium is the most abundant mineral in the body. 99% of calcium is deposited in the skeleton, and the calcium shifts between the blood and bone. The amount of calcium in the human body is about 1 to 2 kilograms, again, most of that being stored in the skeleton. Calcium is an essential mineral for many physiological processes. For example, the release of neurotransmitters from neurons and in the activation of muscle contraction. We'll see more about this in Modules 7 and 8. There, it will become clearly evident why very close regulation is required of this mineral. Just small changes in calcium ion concentration can affect cellular function. For example, again, the release of neurotransmitters from neurons. Those neurotransmitters then can have numerous effects on their target cells. And if calcium levels are out of balance, it can affect muscle contractions. Large changes in calcium can even lead to convulsions and death. There are a number of chemicals produced by different organs that control whether bones release calcium or absorb calcium. For example, the hormones parathyroid hormone or parathormone from the parathyroid gland and calcitriol, which you may recall from Module 5.3 is the active form of vitamin D3, which is made in the kidneys, work together to increase calcium levels in the body fluids. Their actions are opposed by calcitonin, This is a hormone from the thyroid gland that decreases calcium ion levels in body fluids, causing calcium to be deposited in bone matrix. We will discuss these hormones and their regulation in great detail in Module 10. Now, by providing a calcium reserve, the skeleton helps maintain calcium homeostasis in body fluids like blood. This function can directly affect the shape and strength of the bones of the skeleton. When a large number of calcium ions are released from the bones become weaker. When calcium salts are deposited in the bone matrix, the bone becomes denser and stronger. Despite its strength, bone can crack. It can break under extreme loads or sudden impacts, and we call such damage a fracture. Fortunately, because of its ability to remodel, most fractures heal, so long as several components are present. For example, a blood supply is intact, and the cellular component of the endosteum, which lines the marrow cavity, and the periosteum survive. Recall that these layers contain immature stem cells that can differentiate into osteoblasts and therefore build new bone matrix. Despite bone's ability to repair, these repairs can take time, anywhere from 4 months to over a year. There are two broad categories of fractures based on external appearance. A fracture that does not show itself, that is contained within the body, is called a closed or simple fracture. It's completely internal, no break in the skin, and it can be seen only on x-rays. Whereas an open or compound fracture projects through the skin, much more dangerous to the risk of infection and loss of blood. We name fractures by the nature of the fracture, closed or open, simple or compound, and the location of the break. In your clinical note in the textbook, called Types of Fractures and Steps in Repair, we are reminded that fractures are named according to their external appearance, their location, and the nature of the crack or break in the bone. Important types of fractures are shown here in this clinical note by representative x-rays. The broadest general categories are closed fractures and open fractures. Again, closed or simple fractures are completely internal. They can be seen only on x-rays because they do not involve a break in the skin. Open or compound fractures project through the skin. These fractures, which are obvious on inspection, are more dangerous than closed fractures due to the possibility of infection or uncontrolled bleeding. Many fractures fall into more than one category because the terms overlap. Let's look at a few examples of common types. Transverse fractures, such as this fracture of the ulna, break a bone shaft across its long axis. A displaced fracture produces new and abnormal bone arrangements. Non-displaced fractures retain the normal alignment of the bones or fragments. Compression fractures occur in vertebrae subjected to extreme stresses, such as those produced by the forces that arise when you land on your seat in a fall. Compression fractures are often associated with osteoporosis. Spiral fractures, such as this fracture of the tibia, are produced by twisting stresses that spread along the length of the bone. Epiphyseal fractures, such as this fracture of the femur, tend to occur where the bone matrix is undergoing calcification and chondrocytes are dying. A clean transverse fracture along this line generally heals well. Unless carefully treated, fractures between the epiphyses and the epiphyseal cartilage can permanently stop growth at this site. Comminuted fractures, such as this fracture of the femur, shatter the affected area into a multitude of bony fragments. In a greenstick fracture, such as this fracture of the radius, only one side of the shaft is broken and the other is bent. This type of fracture generally occurs in children whose long bones have yet to ossify fully. In a Coles fracture, a break in the distal portion of the radius is typically the result of reaching out to cushion a fall. And finally, a Potts fracture, also called a bimalleolar fracture, occurs at the ankle and affects both the medial malleolus of the distal tibia and the lateral malleolus of the distal fibula. At the bottom of this clinical note, we see the steps in the repair of a fracture. The first step is a fracture hematoma formation, immediately after the fracture, when extensive bleeding occurs. Keep in mind, bone tissue is highly vascular. We often think of the dry, dead bones that we see in a laboratory setting to represent a bone. However, looking at one of these dry models of a bone compared to a living bone is much like looking at a 2x4 to study a tree. There's an enormous amount of blood flow within a bone, And so the first step in a fracture healing is the formation of a hematoma, or a large blood clot we call a fracture hematoma. This soon closes off the injured vessel and leaves a fibrous meshwork in the damaged area. The lack of blood flow kills local osteocytes, broadening the area affected. Dead bone soon extends along the shaft in either direction. The second major step in repair of a fracture is callus formation. The cells of the intact endosteum and periosteum undergo rapid cycles of cell division, and the daughter cells migrate into the fracture zone. An internal callus forms as a network of spongy bone unites the inner edges of the fracture. An external callus of cartilage and bone encircle and stabilize the outer edges of the fracture. Next, spongy bone formation. Osteoblasts replace the central cartilage of the external callus with spongy bone, which then unites the broken ends. Fragments of dead bone and the areas of bone closest to the break are resorbed and replaced. The ends of the fracture are now held firmly in place and can withstand normal stresses from muscle contractions. Finally, compact bone formation. A swelling marks the location of the fracture. Over time, this region will be remodeled by osteoblasts and osteoclasts, and little evidence of the fracture will remain. The repair may be good as new, or the bone may be slightly thicker and stronger than normal at the fracture site. Under comparable stresses, a second fracture will generally occur at a different site. Having completed Module 6.4, take a moment to reflect on the checkpoint questions from the textbook publishers, and join me in Module 6.5 as we discuss osteopenia and aging on the skeleton.